Thanks very much. And thank you very much for the opportunity. This is the first time I've ever given a talk on this. So I apologize if it's a bit rough around the edges. It'll probably evolve over time. So it's sort of an experiment. It's great to see so many friendly faces and some people that I haven't spoken to in a long time. So I'm very pleased to talk about this work. I'm going to present it in a way that I wouldn't have, except I saw Jan give a talk about this and I actually liked, it's not the same talk, of course, but I liked the ordering. He decided to take all of the skeletons out of the closet before he began. And I would like to do that the same way, sort of reveal all of the weak points of the entire framework that we're working within, and then go on to the motivation and the models and so the general phenomenology. Okay, so in that spirit, I'm just going to open by with the fact that this talk is for the applications that we discuss is going to concern eternal inflation. And I think most of us are pretty scared of eternal inflation because it involves the measure problem, invokes the measure problem really, and questions predictability for essentially anything in our own universe. But what we're grappling with, the models don't necessarily require eternal inflation, and I can discuss that later if anyone's interested. But we find it a simpler framework to work within, even if there are these conceptual issues. So most of what I will discuss today really relies on making assumptions about eternal inflation. However, I sort of feel like it's a good time to reopen the discussion about eternal inflation. Of course, there's been an enormous amount of work on eternal inflation for decades, and many very great theorists have worked hard to try and make sense of it. And there's still, of course, many big open questions there. But I think given the LHC results and the way things are working out in terms of sort of symmetry-based paradigms for answering the questions we're interested in, I think it's a good time for lesser theorists like myself who do model building to sort of reopen this can of worms and see if it could maybe shed a different light on the questions that we're asking. Because we're thinking about these questions nowadays in a very different way than we were even 10 years ago. And so maybe inflation and eternal inflation can be a useful tool, or can maybe legitimize some of the things we see in nature that symmetries have not yet been able to explain for us. Of course, inflation has been remarkably successful in my mind. It solves cosmological puzzles like the horizon problem, the flatness problem. And it's also been pretty successful at making detailed predictions for our own Hubble patch, you know, with CMB measurements, the scale invariant spectrum and so on. So I would say in general, inflation is still doing pretty well. As is the stochastic approach to inflation that was developed by Starobinsky, but also others like Vilenkin and Linde and Guth and many others, has been a useful guide, I think, in sort of posing for us as we try to pose the questions that we want answers to. Of course, the stochastic approach is sort of a non-perturbative, almost, when you read the initial papers, almost feels like a very smart guess, but it's been put on firmer footing in recent years by folks who are doing real QFT calculations and calculating how we, within de Sitter space, one can calculate correlation functions, and then taking the limit of the 1-point function or higher moments of that. It seems that the stochastic approach actually emerges from QFT calculations, from proper effective field theory calculations with loops and renormalization and all of that. And so at leading order, of course, there are corrections to it, though. Those calculations reveal corrections to the stochastic approach, but it seems to be capture the leading order physics pretty well. Of course, there's still a lot more to do to understand that. However, this stochastic approach has really raised some very deep puzzles. And one of them is that eternal inflation appears to be a relatively generic phenomenon. Eternal inflation being the fact that essentially once you volume average in some way, it appears that there are patches of the universe that if the slope, for example, of the inflaton is shallow enough, there will be patches of the universe that are always in the inflating regime. Okay, so why should particle physicists care about this? I think it's a good time for particle physicists to care about this because it is sort of telling us that even if one doesn't commit necessarily to certain stringy aspirations, eternal inflation essentially tells us that we're essentially living in a multiverse, that many different things could happen. If you had different fields that control, whose background values control the parameters that we measure in the present day universe, then eternal inflation is telling us that there are all sorts of possibilities that could be there, and different reheated patches could be popping out of the inflation regime at different times, giving rise to different universes. And this is a big, big puzzle, but it's also a big, big opportunity. And the way I like to think of it, that was actually, you know, I think it was Jan in his talk who really clarified this very nicely, is that, you know, suppose you're in a box of gas and you can't see anything, you can't measure anything apart from at one time you measure the velocity of one atom or one molecule. That's just one number. That's well, three numbers if it has if it's a vector. And you measure that and you ask yourself, was that likely or unlikely? But you have no access to the rest of the particles. You have no access to the ensemble. You have really no idea. You measure it and you could say, well, maybe the temperature, if this was a likely measurement, the temperature was of order this velocity, right? Or using half mv squared, temperature was of order this kinetic energy. But you don't know if it was likely or not. It could be that it just so happens that you measured a velocity that was right out in the Boltzmann tail somewhere, and it was completely unlikely. And you actually don't know, right? I mean, you can make guesses, and that's sort of what we're doing when we're staring at the standard model parameters. We're making guesses. We actually don't know how likely or unlikely our measurements are in this sort of multiverse of possibilities that eternal inflation hands us. On the other hand, if that measurer happened to know some of the more macroscopic quantities, and such as the temperature at equilibrium within that box, then this measurer has a context, right? This measurer can say, well, I measured that velocity, and you know that was pretty much what we would expect, given that the temperature is of order the kinetic energy. And so that context really frames our own interpretation of the likelihood of a given measurement. And without that context, we really are blind to how probable or likely any given measurement would be. And by measurement in the context of particle physics, I really mean measuring a standard model parameter. So in my view, you know, if there is a multiverse sort of seeded by eternal inflation, in which parameters are perhaps scanned by background fields, then just by measuring the standard model parameters alone and not thinking about this multiverse, it raises questions about what sort of probability in some sort of quasi-statistical sense we assign to the measurements that we're making. Of course, anthropics can give us some help on that front, but it doesn't help on every front. It works, you know, pretty well for the CC, for instance, but for other aspects of the standard model where we have many puzzles, it doesn't help at all. Instead, you know, if we could start to do statistics on this sort of ensemble of universes, then we can start to assign some sort of context to parameters and start to assign some sort of meaning to what we expect to have measured in our own horizon. Of course, this is very, very difficult, right? And you know, there are skeletons in the closet everywhere, but this is the goal of using or sort of appealing to eternal inflation or the inflationary paradigm more generally. So how do we go towards sort of being a quasi-statistician of sort of the multiverse? Well, it turns out that, of course, these sorts of questions have been raised a long time ago by many great theorists. And the stochastic approach is one way of sort of trying to frame these questions. It's not the only way. There are many, many approaches to this problem, but this is sort of, I think, the simplest one to get your head around. So the stochastic approach basically models a scalar field. If you have a light scalar field in de Sitter, it models that scalar field as being like a scalar field that behaves classically, but with some, so this is this quantum drift term here, but with some random Gaussian noise, which is proportional essentially related to the Hubble constant. So the sort of effective Gibbons Hawking temperature, you can think of it in that way. And then if we had lots of different scalar fields, so this is set up using essentially for one trajectory of scalar fields during inflation, this is set up as basically a Langevin equation. But once you take the average of the results of those Langevin equations, you get the Fokker-Planck equation. This is all stuff that we're obviously very familiar with from Brownian motion, random walks, statistical mechanics, and so on. And this is what it looks like in practice. So you end up with a probability distribution for that field. Again, this is a field that's light, so it's a field that satisfies slow roll, for instance. There's a drift term, which you can derive directly just from the equations of motion. Now, all of this essentially comes from the slow roll equation, phi double dot plus 3h phi dot equals v prime. And you can derive all of this. So you discretize that, and then you get the Langevin version, then you add the Gaussian random noise, and then you can derive the Fokker-Planck. And so the Gaussian noise is proportional to Hubble cubed here. It's quantum, so there's an h bar, that's very important. There's the drift term here, which is proportional to v prime. The greater the gradient, the faster the drift. And this is how the probability distribution evolves with time. And as I said, this can actually be derived, and even there was a paper yesterday, right, that came out that shows that this can be derived from a much, I think for most of us probably, much closer conceptual calculations in quantum field theory, looking at correlation functions and things like loops and so on. You can actually derive this stochastic equation, this Fokker-Planck equation, as the leading order equation that captures the correlation functions, the one-point correlation, the one-point functions. In some sense, this connection with statistical mechanics is not just some sort of unexpected coincidence. I've taken the definition of the Fokker-Planck equation from Wikipedia, and you can see that in statistical mechanics, the Fokker-Planck equation is a partial differential equation describing the time evolution of the probability density function, and it really is the same equation. This is it sort of looks like a heat equation sort of situation. And also we have these connections in de Sitter with effective temperatures, with the Gibbons-Hawking temperature. So in some sense, one can really start to think about this statistical ensemble of patches of the universe during inflation with different scalar field values in a very, very strong analogy to the way we normally think about statistical mechanics. Okay, so what we were interested in is not so much the distribution of the field values as they're walking around. That gives you a probability which satisfies the Fokker-Planck equation. But what we are sort of interested in, and this may not be the right question to ask, but we thought it would think it is. We are interested in the volume averaged version of these, because of course, if the field happens to be performing its random walk quite far up a potential, those patches are inflating more than the patches further down the potential. So one has to volume average these random walks. And what comes out of that is what we called the FPV, which is the volume averaged Fokker-Planck equation. And that's this equation here, which has also been studied a lot. And this is the equation that really drives most of our intuition about eternal inflation, for instance. Okay, so that's the bare bones of the sort of conceptual framework that we are working within to try and sort of grapple with particle physics expectations. One other important aspect is that we are particularly interested in the steady state solutions to this. One can start with an initial condition, also some boundary conditions, which I'll discuss in a second. You start with an initial condition. It could be anything. It could be, a Gaussian, it could be flat, it could be a delta function at some particular field value, and then that will evolve according to this equation. Whilst that is evolving and you haven't reached steady state, then any time you sample from that distribution, the probability distribution is clearly dependent on the initial conditions, because it's still, in a form that depends on what your initial condition was. And that's somehow unappealing, especially in eternal inflation where you've got an infinitely long time to wait. So we were interested in the equilibrium distributions. You can think about these as being like equilibrium in a box of particles, which are then eigenfunctions of the inflationary rate. So they're time independent, which means that the corresponding Fokker-Planck equations would be in that line. If you're doing that calculation, would be the derivative with respect to time would be 0. But here, these are the volume average. So here, the rate of change is just the inflationary rate of the entire ensemble, but the configuration is not changing. So the time derivative is not 0. It's a constant, but it's proportional to P itself. It's the configuration is an eigenfunction of time evolution. And so these distributions are the most interesting because they're independent of initial conditions. It also turns out that they're unique. So once you've specified your boundary conditions, there's only one stationary final state for a given potential, given boundary conditions and this equation. I should also emphasize something which does not get discussed very much in the literature, but is obvious to all of us, which is that this is a second order differential equation. And so you have to have boundary conditions to even start calculating anything. Otherwise you'd have too many integration constants. And they're really just as much a part of the theory as the equation itself. And we won't always explicitly state, or in this talk, sorry, I won't, in the paper we do, I won't always explicitly state the boundary conditions. When I make statements, I'll try to make them statements that are pretty much independent of the boundary conditions that you choose. And when they are dependent, I will mention them. Okay, so that's the sort of the general framework of the stochastic approach. There's some other important things to keep in mind. One is what we call the entropy bound. This is a bound that has been arrived at in many different ways. Guia and collaborators have made some very compelling arguments that arrive at this bound, at this number, and there are papers by Nima and Senatore and Zaldariaga and lots of others, and Dubovsky, also arriving at this bound from different means. But basically, this is something I wasn't totally familiar with before this project, but there's basically a bound on the number of e-foldings you can have occurring before you're automatically in an eternal inflating regime. And this is independent about talking about shapes of potentials and all sorts of things. If you wait for this number of e-foldings for a given value of the Hubble constant, and it's larger than this quantity, which is the entropy of de Sitter space for that Hubble constant, then you're necessarily in eternal inflation. As I said, the applications I'll discuss in the second half of the talk, the ones that we did in our paper, we were all assuming that we were in the eternal inflation limit. For our parameter choices, we were always violating this bound so that we're in eternal inflation. Because of this, I think because of the measure problem that comes up in eternal inflation, which I will come to, once we're violating this bound, it may sort of cause horror and disdain because it calls into question many aspects of being able to calculate and make predictions. On the other hand, the folks from the inflationary community have been saying for a long time that to a large extent, it's not guaranteed, but to a large extent, eternal inflation looks almost sort of generic in inflationary models. So if it's sort of generic, then maybe we have to work with living on the other side of this entropy bound in any case. Okay, so that was the good. This was sort of the sort of bad, which is that there is a regime in which a very simple number which can tell you no matter how much model building you do, if you have this many e-foldings, you're in eternal inflation, which is something I think isn't fully appreciated necessarily. So that's the bad, or almost bad. Now we get to the bad and then even worse. So the first bit of badness here is that one has to choose the clock by which we even register events. Now that may sound unimportant because we're going to talk about stationary solutions, which aren't actually evolving in time anymore. They've been left alone. But whether or not it's stationary depends on the clock that you've chosen. And so you could use proper time, which is what we use, but you could also use different clocks. We sort of parameterize different types of clock because Hubble here depends on the values of the scalar field. It depends on the scalar potential. So one cannot disentangle necessarily the clock and the phi position, the field position, sorry. And so one has to choose a clock. It turns out that before eternal inflation, for any observable that you might want to calculate, largely the observables will not depend on the clock that you choose. They'll be largely gauge invariant. But once you hit eternal inflation, the things that you're talking about all become dependent on the clock. And that's sort of not surprising because observables should be gauge invariant. And when you're in eternal inflation, there are patches of the universe, parts of this distribution that become, that are not observable to any given observer. They don't have access to the entire multiverse. So in some sense, I find it not so surprising that once you're in eternal inflation, the choice of clock, which is a choice of gauge, becomes very important. But nonetheless, this is something that we have to live with. We chose proper time. So that's this parameter psi is 1, because it seemed well motivated in that historically, in the sort of the 80s and 90s, is the gauge that many studies of eternal inflation used. But there are arguments for many different gauges, and also for using completely different approaches and measures as well, which I won't really go into much. But we've chosen. Yep, Tomer.
Yeah, sorry. Quick question. So you were talking about the problems of eternal inflation, but I wonder, are you kind of married in this whole framework to the volume measure? Or because it seems like you're discussing volume-weighted probability. So are you kind of already decided on a measure which we know has some problems, or can you take any other measure?
Yes. So we
do the same thing.
Yeah. So I'll come back to this, but I mean, I think honestly, yes, we sort of are, because for some of the applications, the ones that are perhaps more concrete, we're talking about climbing a potential. And for instance, in scale factor gauge, where you just register events with regards to the number of e-foldings, there's no climbing of potentials. But this is also true for any paper that's talking about, you know, scalar field dynamics and inflation. They're climbing up a potential, right? So yes, we are. I would say we are, but I'll discuss this a bit more. I'll also discuss the problems. Okay. Something that's also bad is that you can actually derive this bound, this entropy bound, from a completely different perspective, which is you can ask the question, when do quantum corrections become so large as to change the classical configuration of the system? I.e., when do quantum effects lead to a large back reaction? Because in that context, you may worry that semi-classical physics, which is what this is breaking down. Of course, this is similar to the page time for black holes. You know, black holes are large classical objects, but ultimately quantum mechanics will evaporate them away to nothing. So there is a point in time where semi-classics may be breaking down. We sort of suspect, right, for black holes that actually semi-classics is largely correct, although there may need to be additional things added into the mix, like wormholes. But this may also be important in de Sitter. Normally, you see here, this climbing the potential is sort of a large back reaction, because you're actually, you know, increasing the energy density by climbing the potential, and it's the quantum effects that are doing that. So that is a cause for concern. On the other hand, and we don't know the answer, it could be that semi-classics is fine. It could be that semi-classics is not fine. It's very hard to tell. One analogy that I think is useful to think of, though, is that there are many places in physics where effective field theory doesn't break down, but quantum effects lead to a change of the classical system. Take, for instance, you know, radioactive decays. Each individual decay can be well described. For instance, if it's a weak decay, can be well described via effective field theory. Yet, if you have just, you know, one block of that radioactive substance on your table, and you leave it there for long enough, it will all decay and completely change into a different block of material. And so that is an example of a case where classically the system is sort of like, and also analogous with black holes. Classically, the system is changing because of quantum effects, but the effective field theory itself never breaks down. On the other hand, it could be that maybe in de Sitter, the effective field theory is breaking down, and string theory or something needs to come to the rescue. Even worse than that is that inflation, you know, reheating occurs when the inflaton sort of passes some critical point. We call it the reheating surface. And we can perform statistics by sort of studying this surface, but it must be regulated. So you must choose a measure. So this is getting to Tomer's question. And the results you get will depend on the measure you chose, because in eternal inflation, the result what we call observables in this sort of quasi-statistical sense need not be gauge invariant. We're taking proper time. Proper time gauge has issues. So one of them is Boltzmann brains, that you can essentially end up either there are two sides of this coin, with during inflation having observers who just spontaneously appear. In terms of entropy considerations, that is a possibility. And so when we're talking about what an observer might see, they might not even be in a universe like ours. It's not clear if it applies to us here, because our models, as you'll see, involve a high degree of instability. Essentially, our basic prediction is that the universe is going to decay pretty soon. And that actually changes, you know, Don Page pointed out that actually changes the whole Boltzmann brain question. A second paradox, which is much more severe, I think, is the Youngness paradox. And this has actually been emphasized to us recently by Andre Linde. And the Youngness paradox is that basically in inflation, so without playing the games that we're going to play with decays and things like this, during inflation, if you use proper time gauge, you actually predict that the number of universes that would be twice as hot as our universe is now, so there would be observers in those universes, is a fact that there are 10 e to the 10 to the 60 more of them than there would be of universes at 2.7 Kelvin. And so this sounds like a flimsy paradox, but it's actually very, very severe, and it's a very robust prediction. Again, I'm not sure so much, we need to investigate now how much this applies to our models, because our models also, inflation isn't just a background, the scalar field is changing, and that's changing the energy density, and it can do things like fall off a cliff, which we will come to in a bit. So we're now currently sort of stimulated by Andre, trying to study these questions in much more detail and take them more seriously. That partly answers a bit more your question, Tomer. I should point out that in scale factor cutoff, then you have no Youngness paradox and no Boltzmann brains. So that motivates the use of, for instance, scale factor cutoff or some of the many other measures that are out there that don't have these problems. I should point out though that from a particle physics perspective, any models that involve climbing scalar fields, climbing potentials are sort of, in my view, maybe I'm incorrect here, but in my view are assuming underneath the hood, whether stated or not, something like a proper time sort of a gauge, because you just don't get these volume effects in scale factor gauge. Okay, and now some things that are just sort of ugly. They're not nearly as severe in my mind, although they may be more severe if you're more of a string theory view. And that's that our scenario will always be deeply in the swampland. The swampland de Sitter conjecture is this thing here. The gradient is bigger than V over m Planck multiplied by a sort of an order 1 number. We will always have very shallow gradients and violate this. But also, eternal inflation itself has problems with the swampland, or not even eternal inflation, just inflation, just slow roll inflation. This is the slow roll parameter here, epsilon, which we know has to be much smaller than 1 to have inflation. And you can see here that epsilon being much, much less smaller than 1 is in contradiction with C being an order 1 quantity. So the swampland itself has inflation has questions to answer when it comes to the swampland conjectures. Also, we're going to have, much like the relaxion, really, really super Planckian field excursions, which also violates, the distance conjecture, which is that scalar fields shouldn't change by more than m Planck. I think these are very important aspects and they shouldn't be brushed aside. I don't know how seriously to take them, but I think they are serious. One interpretation is that maybe the evidence for these conjectures is so strong that we should actually just not consider these sorts of parameter points. Another one would be telling us that if something like this happens, or there's some very shallow slow roll slope that gives rise just to eternal inflation, irrespective of what I'm talking about, maybe telling us something very deep about the UV. So I think it's worth keeping an eye on these things. Finally, sort of a personal view, and this is sort of how I convince myself that I can sleep at night whilst writing a paper like this, is that, when we look to the past, there were many breakthroughs that were made by venturing into incomplete frameworks. The development of quantum mechanics is one example, where there were frameworks that had infinities and sort of philosophical questions flying all over the place, and yet folks sort of ventured in to these, even a model of leptons, right? A model of leptons, Weinberg didn't even know if this model would be renormalizable, which at the time was considered a very important aspect, and he states this clearly in the paper. And so, in my view, given the successes of symmetry-based approaches in taking us beyond the standard model, they were of course incredibly important in taking us to the standard model, but we're sort of a bit confused at this current stage. I view these issues more almost as a sort of a welcome invitation, that there's many open questions here, and that I find that these conceptual aspects are very interesting, challenging, but interesting. And so at the moment, I view them as a welcome invitation. That may be absolute naive stupidity on my part, I'm not sure, but I think one should at this stage have a little bit of license to be bold and go into the unknown a little bit. Okay, so now some quick observations. I'll try not to spend too much time on this because I know the audience and everybody knows this stuff very well. But I'd just like to emphasize that what we do observe, setting all of these questions aside, what we do observe is that nature seems to really like criticality. And I'm going to focus on 3 questions. The thing Tomer mentioned at the start is fascinating, but it's never crossed my mind before. And I've never heard anyone else phrase it in that way either. The first is essentially the CC problem. One could discuss this in terms of the QCD contribution to the vacuum energy, or in terms of the electroweak contribution to the vacuum energy. These are relatively IR questions, and yet their generic values are orders of magnitude above the present day CC. If the vacuum energy contribution from the electroweak sector was sort of as we would typically expect it to be, then the universe would be exponentially expanding or crunching with a time constant at something like 10 to the minus 10 seconds. This is not happening. So it appears to all of us, I think, that there's there's all of these standard model contributions. In this case, I'm just talking about the Higgs, plus some constant that has somehow been chosen in advance, almost knowing about the electroweak phase transition or the QCD phase transition. It knew what was going to happen because, of course, the energy densities then were very different. Somehow this constant knew what was going to happen and was chosen just so as to cancel all of these other pieces and leave us with a much more habitable universe. Of course, the answer could be anthropics. I'm not saying it couldn't be, but setting aside anthropics for a moment, this appears to be a question of criticality. It looks like in terms of the vacuum energy, the universe is sort of balanced between explosive expansion or really totally destructive crunches, which are 2 separate phases, very different phases of gravity, and it's balanced somehow right on a knife edge in between them. So I view this as a criticality question, as I think pretty much everyone does. Puzzle 2 is that the standard model itself seems to want to be in metastability. Everybody knows this very well, so I'll go quickly. But as we know, as we take the standard model values of parameters in RG evolve to large field values, large Higgs field values, the Cortic essentially runs through 0 and becomes negative, which means that the potential in a cartoon sense has this sort of shape here. We have our own local minimum here. This is the origin, for instance, but we could in principle tunnel out to a deeper vacuum. And then when we plot this in parameter space, sort of across order 1 values of what we could have expected to have happened, we see that the standard model is really at a very, very special point in parameter space. So again, and this is a view of criticality, those 2 phases, the IR phase and the UV phase, are completely different. Physics is completely different in these 2 phases. We're in one of those phases, but somehow we're right balanced, parameters have been chosen, so we're right balanced at the point which can live happily in a superposition of these 2 phases, which is, in my view, extremely peculiar, and again is screaming criticality. And the third is, well, I can go really quickly here, but the third is the hierarchy problem, right? If we think about the Higgs sector in analogy to other scalars that we know about, for instance, superconductors in the Ginzburg-Landau theory, we know that as we tune, the temperature of a superconductor, we can get to a point where essentially this effective mass squared is becoming small. We do that in the lab, if we're using a transition edge sensor or something like this. But then if we're at a typical temperature, at a typical point in parameter space, we can calculate what this sort of, mass is not the right word, but I'm trying to sort of force this into particle physics language, that the mass of that scalar can be derived from the BCS theory, which is the microscopic theory. And there are no big surprises. There's some interesting aspects about operator running and things like this, but there are no big surprises, and everything looks order 1-ish in a sort of Wilsonian sense. Similarly, this happens for QCD, right? The pion mass is derivable from the fundamental theory, which is QCD, and everything makes sense. It's a bit light, but we have a symmetry understanding for why that is. What about the Higgs? We don't know, but now we do sort of know, thanks to the LHC, that there's not really much else around. And so, or there's not anything else around. And so it seems like in terms of the microscopic UV completion scale, the electroweak scale is much lower than expected. yet we don't have any symmetries or interesting RG properties to explain why that would be. And so for me, this is like a question of criticality, right? There's some typical value. So whether or not we're in the broken electroweak phase or the unbroken electroweak phase depends on the mass. And it seems like the mass has been chosen such that we're at a very special point, which is not near to the microscopic physics scale. It's like tuning a transition edge sensor in a lab to just sit right at the point of superconductivity. Okay, so now getting sort of onto the meat of the talk. We know that, you know, in sort of very old-fashioned language, which I think is actually very, very useful for particle physics questions, the proximity to a critical point is really signaled by macroscopic discontinuities in derivatives of things like free energies or magnetization and so on. And these discontinuities are macroscopic. You know, they look like, you know, a potential is changing discontinuously. Microscopically, though, we see that that's because the two phases can overlap at that point. And it's not just a question of temperature, right? You know, we know this, for instance, for superconductors, if you vary a background magnetic field, you go across a discontinuity as a function of that background magnetic field. It doesn't just have to be a discontinuity in the free energy as a function of the temperature. It can be in terms of background fields. So the question then is, well, what if there's some background field controlling the standard model parameters? And if the value of this field was maybe varied during inflation, which was the whole point of the first half of the talk, then what happens to it? Where do we expect it to land up once we pop out of the inflationary epoch and into a reheated universe? Okay, so to do this, framing this sort of stochastic approach in a sort of EFT-ish way, we assume that the scalar potential has some large contribution, which is just the background inflationary contribution. And then the rest of the potential is just an effective field theory potential for essentially a PNGB. So there's some coupling scale, there's a decay constant, which defines some sort of field range. We're not assuming that this is periodic. So this might be a portion of a field range, you know, half of a cosine or something like this, but something that has an EFT power counting. And we're also assuming that this, as it varies, in this part, we're assuming that as it varies across its field range, that this part here is much smaller than this. So that everywhere that we have something like a square root of V, we can Taylor expand in this small quantity here. When we do that, that FPV equation takes this form here. P is the probability density. Var phi is the field normalized to the decay constant. So it varies between essentially -1 and 1 across the field range that we're interested in. And then there are various parameters. Alpha controls essentially the size of the quantum effects. It has an H bar in it. And a Hubble constant, the sort of background Hubble constant. Beta is essentially defining the field range. So if the field range is super Planckian and we're in proper time gauge, so this psi is 1, then beta is larger than 1. Big T is our clock, which is just related to time by a constant, and TR is sort of the relaxation time scale. In a stationary state, the solution to this equation will be a solution to this equation here, because the time derivative just multiplies you by a constant because you're in an eigenfunction of the time evolution operator. And so we can tell a lot of interesting things about this equation now that we stare at it in this way. The first is that this is quantifying essentially quantum effects, and this is quantifying volume effects. And so volume and quantum play together in an interesting way. We would expect that if alpha is alpha times beta is larger than 1, then the quantum plus volume effects can be large. If it's smaller than 1, then quantum plus volume effects should be small. They shouldn't accumulate to do too much. And that's what we will see in the end of the day. Another interesting thing is that we can stare at this bit. If we're at a peak, if this distribution has a peak, then at that peak, P prime is small. And if alpha is small, so if the quantum effects aren't very large, then the whole equation will essentially be dominated by this part, giving you essentially 0. And you can check this retrospectively, it works. And if beta is large, the volume effects are large, so the field range is very super Planckian, then you see that essentially this equation is telling you that this term is large, so lambda will have to be approximately equal to beta times omega. So omega, the height at where the peak is on the potential, so omega is a function of var phi, will be entirely determined by the eigenvalue. And that's exactly what happens. You can check this explicitly. So the eigenvalue tells you where the peak will be if there's a peak in the solution to this equation. But this is also all very intuitive, because if there's a peak, that means that the field is all localized at one value of the potential, at one field value, which is one height of the potential. But lambda is just the inflationary rate. This whole solution is inflating at e to the lambda t. And so what that's telling you is retrospectively not very surprising, right? If all of the field is localized at one point on the potential, at one height on the potential, then the inflationary rate had better correspond to that height, because the potential at everywhere, the potential energy, the vacuum energy, is just that value there. So there's a one-to-one correspondence between these two things, and you can see it from the equation or just by physical arguments. There's so that if we solve this equation, for instance, on a line, like we've done here, just on a line, and I've set absorbing boundary conditions at the bottom and the top, essentially the solution has to vanish there. You can imagine it sort of, if the field wanders and it's walk off either of these edges, it just drops away to minus infinity or something like that. Then we observe the following behavior. So in the classical regime, which is that alpha and beta is less than 1, so quantum plus volume effects are still small, we find that the solution gets peaked down at the lower boundary here. And this is largely independent of boundary conditions. You can always force it if you choose sort of rather extreme boundary conditions, you can force it to go up the slope, but that doesn't seem very sort of natural in our perspective. If alpha and beta is larger than 1, then it goes to the top, which isn't surprising. Quantum plus volume effects are becoming important, so this thing wants to climb in proper time gauge. And there's a second regime where alpha squared beta is larger than 1. And in that regime, it tries to get so close to the top that it's actually closer, so the peak is closer to the top than the natural width of the peak, which is essentially 1 in Planck units. And so it crams up really, really far, which means, and this is also not surprising, that even sort of in this sort of very basic sense, NLO quantum effects plus volume effects are still larger than 1, so they accumulate. And in terms of the parameter space, so this sort of defines a sort of sketch of parameter space, which is that in these regions here, when alpha is too small, then essentially the theory is becoming non-perturbative. Essentially, the field range is so big that you can't actually do this Taylor expansion. So all the interesting parameters around here, this is all just very much, these regions here are very much just like solutions to the Fokker-Planck equation itself. You can see that these volume effects are, because beta is small, the volume effect, beta is less than 1, the volume effects are actually largely irrelevant. But the three interesting regimes for us here are this one, alpha beta less than 1, alpha beta larger than 1, all of them beta larger than 1, and alpha squared beta larger than 1. So these are the three regimes I will discuss: quantum, QV, and Q squared V. Sorry, classical QV and Q squared V. But the basic punchline is when you're in the quantum regime, it climbs. When you're in the classical regime, it rolls down. And this is sort of not, this is also consistent with, discussions of eternal inflation that you may see in the literature. It's just in our EFT parameterization, but it's the same statement. On a pyramid, we see the same sort of behavior. So if you plot a pyramid like this, in these regimes, it goes to the top. In the classical regime, it goes down to the bottom. Not surprising. Okay, I should say that we used proper time gauge, but any gauge in which climbing can occur, volume effects can be important. For the next two applications that I will discuss, we expect the physics would be largely the same, because essentially the critical point just happens to be at the top of a potential. The timescales, so climbing may not just be particular to our setup. There may be other measures where this happens. In terms of the timescales, we find that in terms of the entropy bond, which is this TS here, that in the classical regime, the sort of relaxation timescale, so the timescale to get to a stationary solution for generic initial conditions, is alpha beta times TS, and alpha beta is less than 1, so you don't need to actually saturate the entropy bond in the classical regime. In the quantum regime, you do. It goes like square root of alpha beta times TS, so if alpha beta is larger than 1, then you're automatically in the eternal regime, which is why I kept saying earlier that if you're climbing, you're in the quantum regime, and that essentially means that you need timescales longer than eternal of the entropy bound in order to reach a steady state. Okay, so last 15 minutes putting this to use. So the first place to put this to use out of those three examples was the standard model Cortic. So we just imagine the following scenario. So if the scalar potential is just some generic EFT potential, for the scalar field. It has some field range and some cutoff, big M, and some coupling scale. And we assume that the Cortic, you could also do the top UCAWA or something like this, but we assume that the Cortic is also scanned by phi. So there'd be or var phi, so there'd be a phi over f coupling in front of, lambda h squared. And then you can just plot out the shape of the effective potential for phi as a function for var phi as a function of var phi. And at each point, we will put the Higgs at either of the two vacua that it could be at. So there's the Cortic can run through 0. So there's the UV potential or the IR, the UV vacuum or the IR vacuum. And at each time we'll put the Higgs where at any place that it could exist, any place that there's a local minimum. In the IR phase, that vanishes whenever you take the Cortic at the cutoff scale, which we're assuming to be, we call this, M. When you take the Cortic at the cutoff scale to be so negative that the Cortic is always running negative all the way down to the weak scale, then you can only be in the UV phase. That would be this region here. Or if you start with it already positive, then it will run down and become more positive. So there will only be the IR phase here. And then somewhere in between, and because the Higgs goes to the UV phase or the IR phase, that changes the effective potential for var phi, because it just, if this is a linear term, for instance, that just gives you a great big contribution here, which can flip the sign of the gradient, for instance, all consistent with EFT power counting. Of course, if the Cortic starts as a function of phi, starts somewhere that's negative but not too negative, then it can run down and pass through 0, and then you will have the coexistence of both phases. So this is it here. So we're just plotting, we put the Higgs in either of the vacua, and we plot out the effective potential for var phi, and this is what it looks like. And you can see that the critical point where the coexistence of those two phases is just about to stop is actually the top of the potential. Okay, and this is, as I said, we're not playing tricks, fine-tuning some parameter somewhere. You can plot this out in Mathematica or something, and this is what happens, which is unsurprising. It's basically this term here, when the Higgs goes to the UV value, which might be 10 to the 12 GeV or something like this. This gives a large back reaction to the gradient of the phi potential, var phi potential. In terms of solving this equation, we have to solve it on both branches, and falling off here corresponds to an absorbing boundary condition at this point. And also whatever flux falls off here has to land here. So we have continuity. So there's sort of a continuity equation that the gradient here has to account for the gradient discontinuity across this point. Everything that falls off has to land somewhere on the branch below. And of course, the self-organized localization, this sort of climbing behavior predicts that you're going to find the scalar field somewhere at the top of this potential. It wants to get as high as it possibly can. And furthermore, how high it can get depends on the background Hubble rate, because once, say this, if Hubble is much larger than the instability scale, then the Hubble fluctuations are going to kick the Higgs over the edge of the potential, even if there is a local IR minimum at 0 Hubble value. So we have to take that into account. So where this scalar field point actually terminates, this phi star, is actually a Hubble dependent quantity. And so on this plot, I'm showing contours of the Higgs mass and the top mass, and where we are in terms of the standard model and instability and stability. And in blue is the instability scale, so the running of the Cortic, which is being scanned by the changing value of phi in the during inflation. And the black lines are the Hubble scale, so that determines where the highest point is. And the prediction here is that the field will be localized at the highest point it can possibly get to. And so this automatically predicts that you will always find, if this had happened, we would have always found the standard model Higgs potential to be in in a critical region between stability and instability. That's the prediction of the theory. As you vary Hubble, the length essentially of this branch gets longer and shorter, but you will always the top of it will be in this regime. Of course, it depends on the sign that you put here and things like this, but nothing more intricate than that. Okay, so that's essentially one way of sort of motivating from these considerations, motivating the standard model Higgs metastability that we've observed. The next obvious application is to the Higgs. So imagine we scan the Higgs mass squared and not the Cortic. We can still use the fact that the Higgs potential has two vacua, the UV vacuum and the IR vacuum, and we can plot out the effective potential. So say we start on the IR phase where the Higgs is localized just in the normal standard model like vacuum, and then as you vary phi, the effective Higgs mass squared is becoming more and more negative. But once the Higgs mass squared is more negative than the instability scale, there is no local vacuum. Essentially, even though the Higgs Cortic could have run negative, already the mass squared is so large that that scale is irrelevant. So it just vanishes. You can plot the Higgs potential in your mind, right? And when the negative Higgs mass squared has become so negative that it overcomes the Cortic as far out as the instability scale, then it vanishes. So again, there's an endpoint. And then when the Higgs goes out to the UV scale, that gives a large correction to the phi potential here, and also a large correction just from the usual terms to the overall normalization. So you can plot this out. We're making assumptions about signs and things like this here, but nothing more intricate than that. And you can plot this out, and this is what the effective potential of var phi looks like as a function of var phi as it's scanning between the cutoff, between the two values of the cutoff. And the highest point is the point where the Higgs mass squared is essentially at the instability scale. So it's destroying metastability. And this is really, really interesting alone. So the prediction of this would be that, of Sol would be that as the eternal inflation occurs, the scalar would climb to the top, and the top happens to be at the critical point, just at the point where metastability, where instability and at the critical point between instability and stability, which is just here, where essentially this local vacuum in the IR phase is just about to vanish. It's sort of remarkable that this works on its own with the standard model, but it doesn't quite work in terms of what we observe. But what this is using is quite interesting because you can get a large scale separation here. And why that occurs is because the instability scale is set by RG evolution, right? It is changing exponentially as you change, for instance, depending on what the value of the Cortic is at the UV scale, then it will, whatever the UV scale is, you RG evolve down, and where it passes through zero will typically be at an exponentially different point. And this is tuning then the Higgs mass to be at that point. So it's really piggybacking on the dimensional transmutation, essentially, of the Higgs Cortic. It's like a form of dimensional transmutation. It's piggybacking on the running of the Higgs Cortic and the fact that that is just a marginal operator. Of course, in practice, it doesn't actually work because the weak scale is not the instability scale, right? The weak scale is many orders of magnitude below that. So this model on its own doesn't quite work, and we had to add something to it. We called it junk. I think in our collaboration, not in the paper, when we were discussing, because we were so disappointed by adding it, we kept referring to it as junk. Now, I don't think we should call it that because maybe it could do G-2 or something like that. So if there's additional matter, fermionic, so there's chiral symmetry, we don't have naturalness problems. If there's additional matter that's light and couples to the Higgs strongly enough, then it can cause the instability scale to be much lower, right? It essentially, once you RG evolve past the scale of the matter, these new fermions, they will deflect it like the top did, but much, much faster. And so that we can then generate a much lower instability scale. And so what this would mean is that then that you can get the Higgs mass through this model. The top of the potential is at a much lower scale because the instability scale is right around the corner. There are tensions here. One is that we have a little hierarchy problem. Because the standard model has to at least last for the age of the universe, we can't make it too unstable. And so there are bounds from this. Also, it really predicts that the Higgs mass is extremely close to the instability scale, not an order of magnitude or 2 orders of magnitude below that. So there's also a little hierarchy problem, which we could only really accommodate by using a Hubble coincidence. So Hubble would also have to be at around the weak scale during eternal inflation. So this model, the standard model on its own, unlike the previous explanation for the Higgs metastability, which sort of worked, you just add this light scalar and it sort of does the rest itself. Here we have to add ingredients. I'm not sure how I think about that. I guess it's good to make predictions. The prediction would be we should see some new fermions coupled to the Higgs, and they should couple in such a way that the standard model is much more unstable than we anticipated. Okay, So now onto the final ultra speculative aspect. So there's one possibility I didn't discuss. I'm going to try and go through this quite quickly, which is that everything I was talking about was about climbing to the top of a potential. When you're in the classical regime, as I said, typically it goes to the bottom of the potential. So if you just had a line like this, a potential like phase V here, then, and if that was in the classical regime, then you would expect that the scalar field will try and get as far down as it can. And basically the Hubble fluctuations plus volume effects are not big enough. They don't, they're not bigger than the distance that it would classically roll in a given time in any case. So it would naturally want to roll down to the bottom. However, if you have multiple vacua, then that can change. And the reason is the following. So if you, for a range of boundary conditions, so we needed to not assume absorbing, for instance, up here and absorbing up here, we have to inject some flux. This result is not very sensitive to that. Once you're in, it's a one-sided window, so, you know, above some value of flux being injected, so it's, the boundary condition is P prime equals something non-zero, not the usual absorbing, which is P equals 0, which may also be tuned or something. I'm not sure if absorbing is any more natural. We don't need to tune the boundary conditions, but for a family of boundary conditions, what happens is that if you have another phase here and you're injecting flux, it falls off here, and individual trajectories will want to roll down, but those individual trajectories will also have smaller volume effects. They will expand less rapidly. And so what happens is that when you solve the coupled FPV equations, including the continuity of flux as it falls off here and everything like that, what you find is that the field distribution on this branch is peaked here. It's peaked right at the same height on the potential as on this branch. After the fact, we weren't entirely sure why this was happening, but after the fact, there's a very simple explanation for this. If you're in steady state, then essentially the number of patches, the volume occupied by this phase has to be equal to this phase. If you can find patches where you're in this phase, then, and you can also find patches where you're in this phase, if you're in steady state, the relative number of those patches is not changing. And what that means is that the patches that are in this phase have to be, on average, expanding at the same rate as this phase. So the Hubble constant has to be the same in both. And the only way to get the Hubble constant the same in both of them, and it does this itself, we're not putting this in by hand, but the only way to get the Hubble constant to be the same in both of them is if this field distribution is localized at the same height, because the height on the potential is just determining the Hubble constant. And so we find, now of course this happens automatically, and you could start with any initial conditions you want. We find that for these boundary conditions in this sort of a setup, even when this is in the classical phase, you get a strange sort of localization where the field is localized at a height on this potential, which is the same as this potential, even though the point where they're in contact, where there's tunneling between them, may be at a completely different place. And you may not, if you lived in this vacuum, you may not ever be able to see that this other vacuum existed. So this is sort of an interesting observation, but why we find it very interesting is in relation to the cosmological constant. So, so I just said all of this in words. The V branch is in the classical regime and the H branch is very shallow or even flat. What's the potential application? So imagine now we use supersymmetry. So imagine the scalar field. So the background physics, much like the Higgs, can be in either of two vacua. So there's a SUSY vacuum, which is also R-symmetric, and this would be this one here, this vacuum here. And then there's a non-SUSY vacuum, which is non-R-symmetric, which would be this one here. And imagine the potential for phi, it could be like a PNGB. The potential for phi depends on which vacuum you're in. That's just like the pion potential, right? The pion potential when the Higgs is in the IR phase is completely different from the pion potential when the Higgs is in the UV phase, because the quark masses are completely different. It's the same symmetry, it's the same, the same sort of selection rules, but of course, what the pion sees, or whether or not we would even say the pion exists, is completely different. It doesn't really exist in the same way, especially once you have gauge interactions. Nonetheless, so this is a motivation that supersymmetry could and R symmetry could be giving a very flat potential here, and lack of supersymmetry, if you're in a super SUSY breaking potential, could give something that's much more sloped here. Then we envisage that there's some other sector that just drives inflation, so it just gives a constant. contribution. So it would be SUSY breaking and so on, but when reheating occurs, that sector drops down to 0. And when that sector drops down to 0, essentially the axes here would drop down to 0, and this phase H would be completely supersymmetric and R-symmetric, which means the CC would be 0. But it could be that we live on this phase, in which case, if Sol had occurred and there was a light scalar field, it would be localized at the same height as this potential here, which would mean that we would observe in our universe a very, very small CC. And that would only be because there's way out in the landscape somewhere, there's a supersymmetric R-symmetric vacuum somewhere. And that these two vacua equilibrated during eternal inflation. And even though now we would have to perform experiments involving a very, very high energy collider to even infer the existence of that other supersymmetric vacuum, it could have actually driven us to a point where we have a small CC now. There are limits. So for instance, to have the scalar field not rolling fast, the reheating temperature, this height difference can't be too large, would have to be 25 MeV or so. That doesn't mean that the cutoff is 25 MeV. It just means that this little inflationary sector here couldn't have been too high. I can explain why that is in a second. And then finally, this is for Tomer. These models on their own, I haven't added any extra ingredients here. So this is just a scalar potential. So this scalar field would continue rolling in the present day universe. And if it did continue rolling, then that would change, for instance, the equation of state of dark energy, for instance, and fundamental constants and things like that. And so we find that relating all of these parameters together, we find that if the Hubble constant during inflation was more than about 10 to the minus 3 eV, which is corresponding to vacuum energy of order 25 MeV, then alpha squared beta would have to be larger than 1, which means that you're necessarily in a sort of quantum regime. This is sort of, there's a caveat to this, which is this is just assuming that the whole scalar potential was a perturbation of the inflationary sector. Of course, the scalar potential, you can't really separate the two. So it could be that the scalar potential isn't a perturbation and it's just some large scalar potential, in which case this breaks down and that's essentially what happens for the CC application that we did. But nonetheless, this puts interesting bounds on things like cutoff. So if we want a cutoff to be larger than 25 MeV, for instance, for both of the Higgs applications, then we need to be in the quantum regime. One could completely change this if you added some sort of post-inflationary trapping mechanism, which is very easy to do. You can add wiggles that switch on at lower temperatures and things like this. But I remember a conversation, and we discussed it a lot during writing this paper, a conversation with Tomer in Tel Aviv some time ago, where I don't want to misquote, but in paraphrasing, Tomer said, somebody get rid of the damn wiggles or something like this. And so we thought, well, let's just go simple with a very shallow potential that's not rolling now and not add something like wiggles. But I'm sure one could do that to sort of free up a lot more parameter space. Okay, so to summarize, whatever your thoughts are on eternal inflation, maybe these are your thoughts or this, or maybe just sort of interest. I think it's an interesting framework to think about for particle physics, even though there are so many open questions and so many paradoxes, which can limit how we can limit the amount of control we have over the calculations that we're doing. If we do embrace it to a certain extent, I think this sort of localization of scalar fields at critical points, in the simplest case, is just by going to the top of a potential, and that top can be a critical point where we're on the verge of instability, where we are unstable, but we're on the verge of the coexistence of two different vacua from vanishing. Sol could then maybe offer us answers to these questions, which are, I give 3 examples that the standard model seems to be very peculiarly balanced in critical states from a number of perspectives, and we don't really understand why that is. And Sol could perhaps provide an answer which is almost contrary to Wilsonian expectations, which personally have guided my own thoughts and many other people's thoughts for a long time. Okay, so I should finish there. Sorry for running a bit over.
Okay, thank you very much, Matthew, and I clap on behalf of everyone. Questions or comments from the audience? By the way, Tomer left because he said so he didn't.
There is a question in the chat. Maybe we can start with that.
There's also Wang Kiki. He raised his hand. Please unmute yourself.
Okay, can you hear me?
Yes.
Okay, thanks for the very nice talk. I have a naive question. I'm not sure if you explained that in the Higgs naturalness part, why is Cortic coupling not scanned by the apeiron field?
Yeah, so I think it would be, in general, right? Everything would be. So in reality, there would be some, sorry, let me, here. Yeah, so indeed. So if we're taking a sort of an honest effective field theory approach, every parameter would really be scanning by the same amount by some generic function of phi over f. And so we investigated this, and you would essentially end up with the same prediction, even if you scan multiple things at the same time. The top of the potential, this is generically, you can choose signs to make something very different happen, but we don't have to tune for the top of the potential to be at the point in this case where the effective Higgs mass squared is at the instability scale for the Higgs Cortic. However, where that instability scale is would then become a phi dependent question. So phi, so as we change phi, the instability scale would also be moving around. It would be moving around exponentially because of RG evolution. Nonetheless, the prediction would remain the same, that in our universe, if this were correct, the Higgs mass squared would be of order the instability scale for the standard model. If we wanted it to match the observed value of the Cortic, then that instability scale would be around, I can't remember, but like 10 to the 10, 10 to the 11 GeV, which is where the Higgs mass would be predicted to be. In this model with the extra particles, it would also, you would also expect it to scan the Cortic and all of the other parameters and even potentially scan their masses. And ultimately the prediction would be that the Higgs mass squared would be at the instability scale, wherever that happens to be, but it would be sort of, the plot would now not just be these two lines, but it would actually be sort of a twisted contour where we would have to scan everything at the same time. So my expectation, and we actually tried to use this, we thought this might help with the standard model, so we'd be able to do it in the standard model without adding the junk, but it doesn't really work because always the prediction is just Higgs mass at instability scale. So the final prediction wouldn't really change much in my, I expect, or we think, even if it scanned it as well.
Okay, I see, thanks.
Thanks.
Okay, other questions?
Can I ask something?
Yes, please.
So just wondering, this type of setup works for any type of first order phase transition potential. So if in any type of potential that would contain coexistence of two phases, this kind of setup would be generically true.
It could be. So what happens to the first order phase transition in terms of scanning with a scalar field means that that scalar field will have a first order discontinuity, and it even tells you the sign. Yeah. So it'll go like this, but it doesn't tell you that that will be at a peak, because the discontinuity could be like this, so the maximum is still somewhere else, but there's just a discount. You're going up like this, and then it's discontinuous, but also still goes up. So you need that the change, the back reaction is such that that discontinuity is enough to actually totally change the gradient to being from positive to negative. Sort of like the Ising model, right? If you look at, we have this in the paper, if you look at the Ising model, that's exactly what happens. You have essentially a potential that looks like this, and as you vary the background magnetic field, you sort of go into the metastable region, and then eventually it drops, and you go to all of the spins flip, so the potential drops down again. So there is a caveat. Now that's completely consistent with effective field theory. These are all order 1 numbers, and the discontinuity is will be an order 1 number with respect to the gradient that was already there. But if it's an order 1 number and the gradient was 2, then that will only change you to 1. It won't change you to -1 or something like this. So there's always an assumption there, although this seems to be borne out in many physical applications. It could also, you could wonder if it would work for a second order phase transition. And the problem there is that,
yeah, that was exactly, so sorry, that was exactly going to be my question. What happens when you have a continuous, I mean, when you have a second order phase transition?
yes. So the problem with second order is, the reason it doesn't work is that it does, so for a second order, so you can just, for instance, if you just scan the Higgs mass, then you get a discontinuity and you don't do anything with the Cortic, so no first order, you're just scanning the Higgs mass. Then you will get a second order phase transition as the Higgs mass scans through zero. What happens there is that you will create a discontinuity in the Higgs mass, and that will start to change, and that has a specific sign as well, and that will start to change the gradient, but it changes the second derivative by an order one amount in units of the effective field theory. All of these quantities are order one. So that means that it does change. So then that changing curvature in the second derivative starts to change the slope, the gradient, because you're going like this. But it can only create a peak at a place that's sort of generic. It's not going to create a peak close to the critical point unless you've somehow fine-tuned the gradient to be small. So a second order discontinuity, like you would get by scanning the Higgs mass, is never going to give you a maximum, and most of this was about just climbing to a maximum. It's never going to give you a maximum near, hierarchically close to the critical point if you're playing honestly with effective field theory. There may be ways of finding symmetries or something to ameliorate this, but we didn't really find it. We actually started off doing second order, and we were hoping that the second order discontinuity would be enough of a, when we were thinking about things in the wrong way, would be enough of a sort of seed to almost get trapped at the point, because the equation knows about the second order discontinuity. You have to put it in it and it knows about it, but it doesn't really do anything. Still, it seems that in the quantum phase, you just always go to the top. And so it will search out the top, and second order just doesn't get that to be close to the critical point, unfortunately.
Can I also ask, I have even more, a little bit more. What happens if you add, so in the waterfall case, you add two fields, but what happens if you have more intersections? Does the localization change in a substantial way? Like if you had more intersections of different phases, if you had more directions in SUSY, I don't know.
I think it would. So this is one field and two vacua. So
yeah,
that's to be clear about that.
Oh,
but yeah. I think it would change a lot. I don't know what would happen. So imagine you had a different, imagine you just had a different vacuum, for instance, here, that this can tunnel off. I really don't know. I have to say, it's also this waterfall case is very different. Those other things are very vanilla. It just climbs to the top, and the top happens to be the critical point. Both of them, it was a first order critical point because of the Cortic. Here, it's a very, very different story. If we put absorbing and absorbing here, then actually the field would still just be localized down here, and you'd essentially want to have nothing up here. That's the stationary state. And so it also depends on the boundary conditions up here, which is sort of, honestly, it's like an implicit assumption that there's other bits of the vacuum, because what that means is there must be something, we call this the end of the effective field theory range, so this is like the UV. What it means is if you have flux landing there must be some other vacuum in this little toy landscape where the field is tunneling off and landing on the potential. So it's sort of implicitly assuming actually what you're suggesting. If we put other vacua explicitly in around here in the effective field theory range, because of that, I think it could change things dramatically. I don't feel like this, my collaborators might disagree with me, but I don't feel like this setup is very, very robust against structural perturbations like that. I think it would really change a lot.
Okay, thank you.
Okay, so other questions or comments?
Nope.
I have some, or maybe I will, since I feel stupid in asking them, so we'll ask you privately later the coming days.
Sure.
Thank you so
much for having me to give this talk, and also it was a good opportunity for me to give it for the first time. I'm sorry I ran over a little bit. I think I may change some slides or something, remove some slides from the first half after this. I went
Thank
on.
you very much, Matt, for the fantastic talk and this discussion. So